in physics of sound and metric of measuring sound. We'll see also what is noise and some what do we mean by architectural acoustic and why do we need it, how to apply it, etc. Okay, so let's start. So the first slide actually it will explain to you very briefly what is sound. So because if I ask for example Fang Jian Shang Fang, oh sorry Pang, not Fang, Pang. What do you think? What is sound? Pang Jian.
Oh, you're calling me?
Yes.
Sound is energy energy transfer through air particle and the air particle vibration and create sound.
Yeah, very
Something
good.
like
Where did you find this?
High school.
Is your sorry?
High school.
What do you say?
High school.
High school. Ah, good. This is good high school. Okay, so it's actually it's correct what you said. It's a good definition, and it's enough to get your mark if it was a quiz. Okay, so let's see this video. It's kind of it's a good video, even though probably I know it will be lagging, but at least you can hear. Please focus on what you are hearing. So let's start.
Let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms.
Okay, now let me ask some questions. If you were focusing with the video, he mentioned that the speed of sound, because sound travel in the form of waves, right? And the speed of these waves, they are dependent on some variables. What are these variables that will have an impact on the speed of sound or sound propagation in the space? Anybody knows the answer? Quickly, please. You can write or you can talk.
Altitude and temperature.
Yeah, very good. Exactly. So basically, the sound will be impacted by the altitude. The altitude, because because the altitude has a relationship with the pressure of the air also. So when we go up, the pressure will increase, right? So that will have an impact on the sound. And the temperature of the air, it has what to do with the humidity also of the air. So all these things, they can have an impact on the sound propagation in the space, including its speed or intensity. And if you have notes, basically, if there is no sound, if there is no always sound propagation, it requires a medium. So this means if there is no air, like now I'm talking to you, my sound is going in the air to the microphone. If this air disappears, you will not be able to hear me. If you go to the moon, because there is no air, you will not be able to hear me. Even you talk, you do like this, but you will not. I will not be able to hear you. Yeah, and something which is obvious, so sound we cannot see it, so it's invisible compared to visible light. Light we can see it, but sound we cannot see it unless, for example, we apply it to specific material, so it starts moving, so we can know that there is a force. So what is sound? Sound is a form of energy, just like electricity and light. Sound is made when air molecules vibrate and move in pattern called waves or sound waves. I think this definition is very clear, right? So it's a form of energy like light and like electricity, and also the way it moves in waves. This means we can draw the wave, so it has wavelength and it has, you know, things that we did already in lighting. Amplitude of the wave, frequency. So sound also they have frequency. Those they do they perform music. They know what do we mean here. So as you can see now, in this building science class, everything is about vibration. Everything is about waves, either in light or sound, and everything is about frequency. So it's important, as you can see, this Nikola Tesla, he said one day, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. In other words, he's saying here, if you want to find the secret of the universe, think in building science too, and focus in building science too. I hope this is clear. So you focus, please. So we already in the video he mentioned if you drop something in the water there will be waves, right? So similar thing when there is a speaker, unfortunately sound we cannot see it, but actually there will be waves because we cannot see the air. The air is moving. And actually if you put smoke close to the speaker and you increase the sound to a certain degree, you will see that the smoke is moving. There is waves. There is kind of a force is going outside the speaker. And basically, as you can see, of course, when we say waves, it means there is molecules of the air that are moving. Actually, they are not moving from A to B point. Actually, they are are moving this way. But when you see it, when you see all of them, it seems that it's like there is a wave moving from A to B. So similar thing, if you see this point, for example, here, it's not really moving. It's going up and down. However, when you see the big picture, it seems that this wave is moving. So it's like illusion. Similar thing, this guy what he's doing. So basically waves, they are not moving. Just an illusion showing you it's like things that are moving, or the wave is moving from place to place. As you know, we talked already about what do we mean by wavelength. So wavelength is from crest to crest, or top of the wave to wave. So this is very known. And you know the amplitude of the wave is from crest to the bottom of the wave. So it depends on the height. Of course, different from the light, we don't use our eye to hear, but we use our ears, right? So, and ears will not so the sound that you hear will depend on the frequency. So if it is loud or it is very smooth, or all this kind of characteristic of sound that are dependent on the frequency, not like in light. So colors that are dependent on the wavelength, right? Not the frequency. They are dependent on the wavelength basically. So human ears detect frequency from 20 to 20,000 hertz. You know, frequency is in hertz. So this is the threshold, we call it. Of course, other animals like your cat, it can hear things that you cannot hear. Your dog also, if you have one. If you see here, so the human threshold from here to here, so basically 20 hertz to 20,000 hertz, your cat can hear when you are talking, can hear you well, as you can see. I think this is a cat, right? Cat. But actually they can hear more than frequency more than 20,000. So frequency here, you as a human will not be able to hear anything. But your cat and your dog, they are able to hear them. As you can see, dolphins and bats, they can even hear very high frequencies that you will never be able to hear them. And as you can see, dolphins, for example, some part of the frequency, they cannot hear them, but a human, they can hear them. Elephants, as you can see, they can hear other sounds. So when you see two elephants, probably they are talking together, but you cannot hear anything. All right, so any sound with frequency below the auditable range of hearing, less than 20, is known as the infrasound. Remember infrared and ultraviolet in lighting, but this one is infrasound. And any sound with frequency above the auditable range of hearing is more than 20,000 hertz is known as the ultrasound. So when they tell you an airplane is an ultrasound, so basically the frequency of sound is more than 20,000 hertz. It's good to take notes because there is a high chance I will do another quiz for you regarding acoustic. Okay, if you have any questions, anything is not clear, let me know also. So threshold, what do you mean by it? Is the strength, the strength at which, or the strength at which a human ear can perceive. When we say threshold of hearing, it means weakest sound that a human ears can detect. Human ear can perceive a wide range of sound pressure. We will talk about what do you mean by sound pressure. So within 20 micropascal, so 10 power minus 6, so it's micropascal. Okay. And there is threshold of pain. So remember, threshold of hearing, threshold of pain. So threshold of pain is strength of sound that human ear can tolerate. So after that, you will start doing like this. You will not be able to hear, you will not be able to support. You know, sound, they use it even to punish prisoners in some countries. So they increase the frequency of sound until it reaches threshold of pain, so it will be really painful for them. So this table shows common sound and or noise in terms of micropascal. So this is the source, and this is how much micropascal. So this is the sound pressure, the unit of sound pressure. Of course, this one is the biggest one. This one, soft sound the human can hear. So 20 micropascal, we mentioned this already, until 20,000, until this one. Normal conversation, like I'm talking now. So the sound pressure is 20,000, about 20,000 micropascal. One second. Sorry, I'm mistaken. So here, remember here, it's about the hertz here. Things regarding hearing, it's about the hertz, the threshold. However, this one, they are about, basically we can hear these one. They are not hertz, so micropascal. So it's not about frequencies. This one is about the sound pressure. Normally there is a threshold here. I'm not sure if it exists in this the next slides. We'll see. But anyway, so for launching of space shuttle, of course you will be able to hear this sound. It's not frequency. Remember, this one is micropascal. So it's really dangerous. Of course, you can even die if you are close to the source of this kind of sound pressure. You can imagine what do you mean by full symphony orchestra, so 2 million micropascal. So now in the video, in the very first video, they mentioned that sound it's propagate in the space in the form of a sphere, right? So in all directions. It's not only in the surface or only on the Y and Z plane. So it's a sphere. For example, me, I'm talking now, so there is a sphere of sound is going outside. Even though there is some kind of sound, for example, when it is a road, the sound propagation, they take it as a cylinder going through the road, not sphere. But when someone is talking like this, it's a sphere. So that's why there is what we call it longitudinal wave and also transverse wave. So what is longitudinal wave? So it's a wave which is in which the motion of the individual particles of the medium is in direction which is parallel to the direction of energy transport. So it's very clear, I think. So it goes horizontally, you can say. So, and when it goes horizontally, if we see it, so the results of such longitudinal vibration is the creation of compression and refraction within the air. So this, one second, someone is calling. Sorry about this. So when we're talking about longitudinal, this is longitudinal, right? So there will be compression and rarefaction. So as you can see, what do you mean by rarefaction? So it's exactly the opposite of compression. So the molecules, when it is compression, as you can see, they are very compressed compared to this rarefaction. And this kind of things, it will make the wave propagate in the space. Now, the other one is the transverse wave. So vibrating object will produce a sequence of compression and refractions in the air surrounding it. These small fluctuations in the air pressure travel away from the source at relatively high speed, gradually dying off as their energy is absorbed by the medium. This is more. This slide is clearer maybe compared to the previous two ones. So what do you mean by longitudinal waves? So these are the waves, and now we are seeing it's like this is the wave, and like the camera is here now. So what you are seeing, as you can see, molecules actually they are just moving doing kind of, they have frequency. They are just moving right and the left, each particle. And this wave, it takes opportunity of this, the movement of this particle this way until to transmit the sound from here to here. So as you can see now here, it looks, the wave, it's moving. Now if we do a section here, so we will see the transverse wave. So it's doing like this also. Here, this one. Of course, these waves, it's like here an example of water. So basically here is a combination of both of them. So basically each particle is kind of, it's making a circle. However, when you see the big picture, it's like there is a wave moving. Similar thing happens to in the sea. So in order to hear, as you know, always there should be three things they play a role in hearing. The first thing is the source of sound. So without this, you will not be able to hear anything. The second thing is your ear, so the receiver. And the third thing, which is very important also, is the medium. So without a medium like air, generally is air when we are talking, or in architecture, generally is air. So, so three things. Now, like what we did to the eye, since the eye is the gate for the light to our body, so this is the gate of sound to our body. So this is, as you know, maybe it has three parts. So the outer ear, middle ear, inner ear. So each one, this one is kind of the receiver, so it collect and channel sound to the middle ear. So just a receiver like this. After that, so the middle ear transforms sound wave energy into the internal vibration of the bone structure of the middle ear. And after that, the inner ear, which has connection with the brain, so transfer compression wave energy within the inner ear fluid into nerve impulses, which can be transmitted to the brain. This slide seems to be like a medicine class, right? So basically, you know, there is fluid normally here in your ear. So there is fluid which can receive the wave energy of sound, and then it will be transferred to the nerve impulses, which in the end will be transmitted to the brain to read the data in this kind of waves. Of course, all these things, they happen in a blink of an eye, so things, they happen very quickly. So why many they switched off the camera? Are they better than the other ones, or what? I can see now only 6 they are switching on the camera. You want to see yourself? So the other ones, they are absent. Okay, I will take notes of these and I will make them, because there is nobody in the class. I cannot consider those, I don't see them in the class like this. Do you think it's okay to come to the class like this? Yeah, I will keep an eye on this. I'm seeing you here anyway. So, how does sound travel? So start with mechanical movement like banging a door. Movement causes vibration in molecule around them. So the vibration among the molecule help sound to travel. This is what we already mentioned. So like let's imagine this is the air molecules. If you blow in these air molecules or you make sound, actually they will take the energy in this sound and they will transfer it in the form of waves until the other one will receive this energy, which is where the your ear is able to translate this kind of energy to sound and words. If you remember, probably one I don't know, in the past the kids they used to play this game. So it's like they create a phone with two kind of boxes or two
They use paper cups and the string.
what?
Paper cups.
Yeah,
They
yeah,
use
yeah,
paper
yeah,
cups.
yeah, yeah, yeah. Using paper cups, it can work good. And as you can see, there is a line, there is a wire. So why there is wire? Because actually, in acoustic, as we mentioned, always there should be a medium. Because now, if this one talk here, actually the sound can follow this medium. So vibration will go through this wire, depending on the material, of course, of this wire. So it can probably transmit the sound. So it depends. Always, vibration has a very high relationship to the material or the medium where it is moving. So this way, actually, if you cut this wire, you will hear less. This lady will be able to hear lower compared to before because of this medium. Now, so sound need a medium to travel. Sound is wave vibration that travels through three states of matter. So solid, liquid, and gas. So all these mediums, sound can move, right? So solid, like in architecture, if you hear. So like in architecture, if you hear, for example, you are in a room, you still can hear the sound of cars outside, for example. So there is some wavelengths, sound waves. They manage to go through the air and then go through your wall and come to your ear. So for sound, it's not like light. If it is 100% obstacle, not transparent, it will stop. So sound, it can move. Of course, liquid, even in water, if you are swimming, you still can hear. Of course, less compared to normal situation, but you still can hear. Uh, and gas, so or even air. Now because as you can see now, the very big difference between sound and lights is that sound we cannot see it, but light we can see it. So now that's why in the next video we'll see a video which shows it's like some people they did an experiment to make kind of to make sound visible. How can we make sound visible? Do you know how can we make sound visible? Okay, so I will play the video to know how did they make the sound visible. I will. Someone, I need to take parcel. I will come after the video, so don't worry. Sorry for that. So I hope you have watched the video, right? It's just 2 minutes. So basically, as you have seen, they did this experiment to make the sound visible. Come on. Because they know when you change the frequency of sound, so this means the wave will change, right? You know, the number of, like here, for example. Like here, for example, they are producing a specific sound with a specific frequency to create certain kind of waves based on the frequency of the sound. And sometimes, like here, they combine different waves. If you can see here, you see this wave moving sometimes. So in this way, in this experiment, they were able to make sound visible somehow. Anyway, so now property of sound. Sound is pressure, wave, and thus cannot exist in vacuum. So if you go to the moon, you will not be able to hear anything. Sound waves can travel through solids, liquid, and gas. You have to remember all these. For a sound to exist, two things are necessary: source and medium, and of course the receiver also. As you know, the sound travels very fast also, but when you compare it to light, light is always faster, right? As you can see also, sound behaves very similarly to light. So actually, when there is sound is coming, it depends on the material. Some amount will reflect, some amount of waves they can be absorbed also by the material of the walls of your building. So this reminds you of light. So light also, you know, depends on the material. Some will reflect, some will be absorbed depending on the transparency. So the laws of light, you can say they are similar somehow to sound, or the other way around. Yeah, similar also to light, always we have different sources of sound in a building. So for example, this space, this one is talking, other person that are talking. So this one is talking to this guy. These are talking. Maybe the air conditioner noise here, background noise, maybe there is a highway. So too many sources of noise, of sound and noise combined will be in the space. So again, we talked about the wave characteristic already before. So this is the amplitude and this is the wavelength. So I think everybody knows and remembers what do we mean by amplitude of the wave and the wavelength here. And frequency, we talked about this in lighting as well. So which is the number of cycle of vibration per second. So the unit is hertz. And when we talk about the frequency of sound is often connected or related to the pitch of sound. So when an object that produces sound wave, it vibrates 100 times per second, sound frequency is 100 hertz. So this is the pitch. So the pitch is the frequency of sound perceived by the human hearing. When we say low pitch, those they perform music, they know we mentioned this low pitch and high pitch. So low pitch is caused by low frequency sound waves. High pitch caused by high frequency of sound waves. Here are two different sound waves, and as you can see, there are different in terms of frequency and amplitude also. As you can see, this one is just here, but this one is the double. So 1, 2, 1, 2. Okay, here there's a software just to do some simulation regarding to explain more here. Look, in this software there is the frequency. So as you can see, we have a speaker here and we have a human here. As you can see, we have frequency and we have amplitude. So basically we have the two variables that we need to play with regarding the sound wave. But there is no wavelength here because wavelength is not that important. Wavelength is important in lighting, but here frequency and amplitude are more important. Now I will try to simulate when I start changing the amplitude and the frequency. You will hear the sound, how it will change. So to get an idea. I hope you can hear some sound right now, right?
Yeah, the
Okay, now look when I increase the frequency. Or let me lower the frequency. Almost nothing happened, right? It happened, but you see, when you remove the frequency, it means basically there is no wave, because you know the wave, it has waves, and zero frequency, this means there is no period. As you can see here, I will increase it slightly. You see now the wave, wave length is too big. You see, from black to black here. So the white is the peak of one wave. So if you do a section, I mean, I will bring this to here. You see now how many, when we increase the frequency, you see how many waves? You remember when we increase the frequency, it means the wave which should be repeated very fast in a specific time. In 1 second, it can repeat many times, as you can see here. After that, I will start changing the amplitude and see what will happen. The amplitude of the wave, of course. Now, as you can see, it's here, the middle. It seems it's like the amplitude is increasing the sound, right? Just we are increasing the level of the sound. As you can see, when the more I increase the amplitude, the black will be very black. It's like we are, you know, the amplitude, the wave is doing like this. So when I increase it, it will go up and will go down. I'm increasing that up and down. I know it's very annoying, right? Okay, let's see other things. I think no need for this. Look now, when there is two sources of sound, as you can see, sound will mix. As you can see, they are mixing together. So this part is a mix of sound from this and this. Be careful. If your mom comes to you, she will tell you, are you playing or are you studying? Okay, let's see this one. This one is regarding reflection. As we mentioned, sound reflects, right? So when there is an obstacle, it will reflect. And of course, it depends on the angle. For example, here there is wall angle. and wall position, frequency. Well, this one already we did it. So the frequency is very low now. But when I increase it, so the vibration would be very fast. Now, regarding as you can see, there is a speaker is inside the room, and you are here, the listener, right? So I will switch on the sound, and I will listener. Look, when I can remove the air in the box, look what will happen. You see the pressure is decreasing. It means there is less air. So basically, as you can see, we cannot hear anything. Even if you increase the amplitude, since there is no air, there is no sound. There is no medium, there is no sound. Okay. Okay, this is just for illustration. So basically, those they play with the piano, probably they know what do you mean by octave, this octave. So here's the definition. So most sound contains a combination of many different frequencies, like music, for example. Hence, it's usually measured and analyzed in a range of frequency in one group called octave. So those that use music, they know there is different octaves in the piano. For example, from C to this C, there is one octave, or from C to B. So the end of the octave is until B. So basically, there is, I think, 12, so 5 and yeah, how much? 6, 7 and 5. So 5 bottom. Anyway, so basically the definition of octave, so a range of frequencies from a given frequency to the double of that frequency. So for example, when we say, for example, let's say this C, the frequency of when you press it, the sound which will come out is 880, sorry, this C, I mean this C. Let's say it's 880 hertz. So it's one octave above this one. So this one should be 440. So just the double actually. If you see, for example, if you compare now here, so you see this is the third octave and this is the fourth octave. So C3, so this is the frequency. If you press this is the frequency of sound. You will get it. This one, C4, after one period or one octave, the beginning of the next octave is the double of this. So the sound, it's like a coding of sound to know this is the double of the frequency of this one. So the piano, of course, all these they are applied. So it's not random sounds each one. So they have principle. That's why they use octave. So again, octave range of frequency from a given frequency to the double of that frequency. I hope this is clear. Is it clear? You can just compare. So the fourth octave, B, for example, as you can see, is the double of the previous one. The same, you can say the same button, but in the previous octave. There is another phenomena in sound which we don't find in light, and this is very important, and we call it resonance. So you have to know that every object has a natural frequency. By a natural frequency, we mean characteristic frequency at which it tends to vibrate when disturbed. Also depends upon factors such as the shape, density, and stiffness of the object. And when we say acoustic resonance is a phenomenon in which an acoustic system amplifies sound waves whose frequency matches one of its own natural frequencies of vibration. In other words, for example, I don't know if you know this game or not. For example, if I take my hand like this and I just blow air like this, as you can see, nothing interesting is happening, right? But when I make special room here like this, I make special room and I blow like this, as you can see, there is an interesting sound. So now this room that I created here is resonating with the frequency of sound that I'm giving. So it's like this room has natural frequency so when you give it that natural frequency, it will vibrate. Like now I give, it's like my air blowing and the frequency of this, they resonated together. So sorry about that. Okay. So no, this is another video. It's good when I need to go down. The slide of the video comes. So now we are talking about resonance, sound resonance. So actually, in the next video, it will show you when you apply a specific sound to a glass, a cup of glass. So when you apply a specific sound, which resonate with the natural vibration of that glass, that glass will start vibrating, only using sound, and it will explode.
Where you can actually, if we can find the resonant frequency of a wine glass, so that's its resonance frequency. It's
Right, that note is what you want to achieve, yeah?
If you force it to vibrate at that frequency, then it will vibrate so violently that it will break.
Fabulous, great. I'm into that in a huge
theory,
way.
sorry, I meant to say in theory.
Yeah, no, let's just keep doing it until we get to break. I'm very happy. Is everyone ready? Is everyone ready? Their fingers in ears or something on? Yeah, yeah. By the way, to say this is a trick that was used to be done by opera singers, wasn't it?
It's actually really difficult to do.
Yeah.
And to do it, you have to, if I just nick it for a second, you have to get it that close to your mouth. And as we shall see in a moment where the glass goes, if you like glass in your mouth, it's a really stupid thing to do.
Okay. So we know we're at the right frequency if we get the piece of paper to
That's going to vibrate the glass, which will make the paper jump.
So the minute we know the paper's jumping, you just crank up the volume.
Right, okay, you ready?
How exact do you have to be here?
Well, very exact. Can you see that going?
Yeah, I can, yeah. That is spooky. Wow. Loving the tension of the build-up. You took long enough to get there, didn't you? We actually, you did one with a proper high-speed camera.
Zoe Laughlin from our institute, she did one a few years ago with a slow-motion camera, and this is it.
Wow, wobbles quite significantly. Bottom bit goes first. How is the top bit holding together?
Yeah, that's incredible. That shows you just how fast the frame rate is.
Imagine if that was near your mouth and what's traveling that way.
Yeah.
I'm very sorry. Sorry again. So have you noticed? Have you seen the video? So basically using sound vibration which resonate with the natural resonance of the glass, they were able to explode it. Okay, let's continue. So this is the same thing. For example, this one is not related to sound, but actually if you do this experiment, you take a stick of wood and you connect other stick of wood but with different heights, and you connect balls here, and when you start vibrating with a certain frequency, this piece of wood, you will notice when you increase the frequency or you decrease it, sometimes some balls, they will start vibrating too much. So for example, as you can see, this one, it will start vibrating too much. That time it means the natural resonance of this one, which is the red one, is resonating with this frequency here. Uh, so I think you know we did this before. So the velocity when we regard the frequency. So velocity, it's equal frequency multiplied by the wavelength. We did this in lighting, right? So you know this. So when we say, for example, here is an example, a particle sound wave has a frequency of 440 hertz and the velocity of 340 meters per second. So if you ask you to calculate the wave length of this sound wave, so what is the wavelength? So basically the wavelength is velocity divided by frequency, right? So it's very easy. And so this is the wavelength, so 0.773 meter. Now, this slide is very important. Always, as an architect, you should not. Where they are other students? Are they absent? Where is Merit? Where is Merit and where is his friend? They're absent? Okay, I have the right to make those they didn't show up as absent anyway. So I mentioned that there is this sound level, the unit is decibel, is one of the very important metric that you have to know, and you should not forget. And this sound level can be converted to power, sound power, or sound intensity, or sound pressure, or sound exposure level. Okay, let's go through all of them. Basically, the sound level, you know, it's.
So we can see the slide. Sorry. We can't
Sorry?
see the slide. We can't see the slide.
So what you can see now?
Now okay already. I think just now it's lagging.
Okay, now you can see the slide, right? So it's written sound level here, right? So you can see the slide right now, sound meter here. So similar to lighting, you know, lighting we use the lux meter to measure the luminance, right? For sound level, that is what we call it sound meter. So we measure the level of light, sorry, the level of sound, not the level of light, and the unit is decibels. Of course, you can download. There is many applications also. They measure the sound, and basically instead of using, they don't use sensor, but they use your microphone in your phone to measure the sound level. And of course, there is the either your phone or this one also is more professional. As you can see, there is a difference here. They are comparing here. There is a slight difference. So previously they used to measure the sound level using Pascal, which is the pressure, sound pressure. However, this unit could involve some unmanageable numbers, so the decibel or dB scale is used. So the scale uses the hearing threshold of 20 micropascal to 20,000 10 power minus 6 Pascal as the reference level. This is defined as 0 decibel. So 20 micropascal is 0 decibel. So you can convert between the two scales. Now regarding the intensity, because we have seen intensity here, right? Here, the intensity. So the intensity is the power carried by the sound waves per unit area in a direction perpendicular to the area unit, W watt per meter square. And this is one of the laws that we use to calculate the intensity of sound from one point to another. So basically, I1 is the intensity of sound at point 1, I2 is the intensity of sound at point 2 is equal to d, or distance at point 2 square, over distance at point 1 square. Okay, let's see what do we mean. For example, if you give you an exercise like this. So as you can see, we have one source of sound. When we measure the intensity of sound at at 10 meter far from the source. So we found it's 3.5 multiplied by 10 power minus 6 watt over meter square. So this is intensity at point 1. As you can see, the intensity of sound at point 2, it is not the half, even though we just multiplied 2, the distance. The intensity it will not be just divide this by half. You have to calculate it using this law. So this means you just apply I1, which is the intensity at point 1 here, divided by I2, intensity at point 2 here. We don't have it, you are looking for it. And it's equal to distance at point 2 square here, 20 meters square. The over distance at point 1, which is 10 square. After that, you take the I2, the intensity at this point. If you do the calculation, you will find it's 8.78. As you can see, multiplied by 10 over power minus 7. So it's less than this. But it's not the half. So this means when you double the distance between the source of sound and the receiver, the sound intensity, it will not decrease by the half also, or it will double. It doesn't work like that with sound. Because sound behaves in algorithmic way. If you see here, it's written already in this slide. Various logarithmic measurement of auditable vibration. So I hope this one is easy, right? So the intensity, how to calculate the intensity, because in assignment, if you check assignment 3 in CN, I asked you to do this question in assignment 3. So you have actually to calculate the intensity at the point. Is there any question regarding this? Okay, if there is no question, I will give you a question. Now, if I ask you, okay, now we got the intensity of sound at a point which is far 20 meter. If I ask you, what is now after, if I select a point which is far from the source 30 meter, how much it will be the intensity of sound? So 20 meter, we got the result. What about 30 meter? What about the point here, which is 30 meter far? So basically, you just apply this law. So point, you can select either this one or this one. You can select, for example, let's say we select at point at 20 meter far from the source is this one, right? So this one is D1, it will be D1 square here. And now 30 meters, so D2. D2 is 30 meter. Intensity 1 is the one that we got it, this one. Intensity 2, the one that we are looking for it. Or we can make it intensity 3 and intensity 2, this one. I hope this is clear, right? I think it's very straightforward. Now, the one that we did before, it was the intensity of sound. And remember, the definition of the intensity is this. So the power carried, by sound waves per unit area in a direction perpendicular to that area. Now, from that sound intensity, we can get the sound level. Maybe at least the difference of sound level from point to point. So remember, we calculated the intensity here. So I1, sorry, we have it. I2, we calculated, right? After that, actually, in order, if you want to know the difference of sound level from this point to this point. For example, I tell you at this point, let's say it's 40 decibels. This one, we don't know it, the sound level. I tell you how much is the sound level here. So this X, how much? So basically what you have to do, you have to use this equation. So the sound level at point 1 minus the sound level at point 2, which is X minus X, is equal to 10 logarithmic of intensity 1 over intensity 2. We calculated both of them. However, to make it, because we can take the intensity 1, which is this number here, over this one. However, since it's a complicated number, and since I1 over I2, as you can see, it's equal to D2 divided by D1. This means we can just take the easy numbers to apply the logarithmic equation here. So that's why, as you can see from here, we went to here. So instead of I1 over I2, we use D2 over D1 because they are equal in the previous law. So basically it will be 10 logarithmic 20 square over 10 square. If you do the calculation, you'll find it 6.02 decibels. Now if I ask you how much now, how much is the level of sound at this point? We did all the calculation. Now give me how much is the level, sound level at this point. How much? Loom when?
Yes, sir.
So how much is the sound level at 20 meters far from the source? Sorry?
6.02.
No. This one is, as you can see, calculate the decibel level change between the two positions. This amount is the difference between this and this. It's not, it's reduction of decibels. As you know, the level of sound at the 10 meter will be higher than at 20 meter, right? It will decrease when you go far. So now how much? And they give you this one is the level here at this point is 40 decibels. So the question is how many decibels here? After 20 meter.
34.
Sorry?
33.98.
Exactly, yeah, exactly. So basically 40 minus 6.02, which is the difference. So as you can see now, we started by calculating here the intensity. We used this law, which is very straightforward. Very easy. I think everybody can apply this law. After that, we have another law which says the intensity at the level of sound at point 1. Point 1 usually is the closest one to the source of sound, so it's here. Minus the level of sound at point 2, which is after far 20 meter, it's equal to this. So basically there is a law we have to apply. So the thing that you find is the difference, and it's not the level, the sound level at this point. Is this clear? So now, as you can see, if there is a source of sound, after 10 meter, it was 40 decibels, for example. But after 20 meter, the level will not be 20. It doesn't work like that with sound, because it follows a logarithmic function. So basically, as you can see, the reduction now is only 6 decibels, even though we doubled the distance. So this is the magic in sound. So it doesn't really work just you double the distance, you just divide it by 2 the sound level. Okay, let's continue. Well, these ones, you know them, you know, logarithmic of 10, base of 10 of 1 is equal to 0. So this is just to remind you, because sometimes things that are easy but you forgot these things, the result will not be correct. Okay. Sound measurement, adding sounds or noise together on a decibel scale. If two different sounds arrive at the same time, then an ear is subject to pressure waves. As you have seen in the illustration, waves, they can be combined together. Doesn't mean if the wave is coming like this, another one is coming like this, they will stop here. They will be immersed actually. The addition of sound levels in decibel does not give the sound level of combined sounds. This is very important. So this is the example to explain. Total sound level caused by the combination of two vacuum cleaners at a decibel of 90 decibels will not give 180 decibels. So sound level doesn't mean, for example, if my phone starts ringing in 20 decibels, if the same phone starts ringing in the same time, it will be 40 decibels, the sound level. No, it will not. It doesn't work like this with sound. But in light, for example, if there is, in light, if you take a lighting fixture, the luminous level, let's say this light is producing 100 lumen. If you double this light, yes, so 200 lumen it will be. But sound, no, it doesn't work like that. Okay, let's continue. Yeah, this is very important actually. So basically, this slide is just to explain to you that there is, for example, when there is 3 sources of sound, if you want to calculate the level of sound, for let's say this is the room, and there is 3 sources of sound. Let's say there is a baby who is crying, and there is a phone which is ringing, and someone who is singing. So if you want to calculate the level of sound, you cannot just go, okay, this baby is crying, okay, 30 the sound level is 40 decibels. This is phone is ringing 20. This guy is singing another 40 decibels. So, okay, so you just sum them. No, it's totally wrong that way. So basically you have to use this equation. So here is an example. So adding 60 apple to 60 apple result in when 20 apples. But this is not the case with sound when they are expressed in decibels. In fact, adding 60 decibels to 60 decibels gives 63 decibels. If you combine two sound levels 60-60, the result of sound level is 63, not 60 plus 60. So the following formula explains the general principle of adding sounds on the decibel scale. It's not that complicated actually, you need to be careful when you are applying it. I will show you an example and after that I will give you an exercise. For example here. So here is the equation that we use always to combine two or more than two sound sources, sound level. So here, for example, we have three sound sources. The first one produces 60 decibels, the second 65, and the third one 70 decibels. So now if I ask you how much is the sound level in this room, so what you have to do, you have to take these numbers and you put them here in this equation. So 60 decibels. Of course, you can calculate this first, because you see we need to divide by 10 for each one. So we divided by 10, so 60 divided by 10, so 6. After that, we applied the logarithmic. Sorry, 10, not logarithmic, this one. 10 power the number that we got here. So that's why it's 1 million here. We do the same thing here and here. After that, you sum all these numbers together. So 10 power the sum of this. So you find this number. After that, you apply the logarithmic of 10. Remember, this is logarithmic of 10 to this number. We will find 7.15. After that, you multiply by 10. As you can see, there is 10 here, so you multiply by 10. As you can see now, so the total or the combination of these sound levels, 60, 65, and 70, they produce only 71 decibels. This means if a room contains three light, oh my God, I'm just repeating light. If room containing three source of sound, 60, 65, and 70, if you bring a microphone and you try to measure the sound level that within that environment, you will just find it 71. You will not find it 60 plus 65 plus 70. Okay, is this clear? Yep, G Loom, is this clear, right? Yep, clear. Okay, since it's clear, I want you to do this. Let's say we have 30 decibels. One source is 30 decibels, one is 55, and one is 65. So how much is the total sound level in the room now? I'll give you 6 or 7 minutes to do it. And I will ask everyone to let me know what is the answer.
Are you sure it's 6.54? Someone said it's 6.54. I don't think so. It means it's like imagine you have a sound level with 30 decibels, 55 decibels, and 65 decibels. And then it's like when you combine 3 sounds, for you reduce the sound level, yeah, multiplied by 10, yeah. This one is, yeah, 65.4, yes, should be okay. Okay, I don't know, I didn't do the calculation, but it's logical. Yeah, but the first one is not logical. All right, so I think it's easy, right? But the most important thing is not just to do the calculation. It's important also to be inspired and to see, oh my God, okay, when we add the level of 3 sounds, it's not 1 plus 2 plus 3. Actually, it follows an logarithmic behavior or function, which is this one. All right, so let's continue. So now we'll jump to noise. So what is noise? So simply it's any unwanted sound. So as you can see, it's very subjective. For example, some good music for you, probably there are noise for others. So it's very subjective. As you know, nowadays actually noise has become a very big issue, especially those they live in the cities like Kuala Lumpur here. And as you can see, there is many type of noise, especially this highway and railroad, and of course power plant noise, etc. So all these, they bring noise to the interior space and to architecture. In more detailed definition, so noise is any sound that is distracting, annoying, and harmful to everyday activities such as work, rest, entertainment, study, and so forth are regarded as noise. In fact, any sound judged by the recipient as undesirable and be considered as a noise, can be considered as a noise. Okay, this is, I think everybody knows what's this. So here are some factors that the sound that can influence the sound. So frequency, continuity, variation in time with time of occurrence, information, content, origin of the sound, background noise level, loudness, recipient state of mind, and temperament. So if someone is sick, for example, if some even normal discussion can be annoying, can be considered as a noise for him. So let me jump. I think this slide here. So as you can see, similar to illuminance, you know, illuminance, we measure it using lux. So here, the sound level, as you can see, we measure in decibels. And as you can see, 60 decibel, 65 decibel, it's like normal conversation, so it's around 6. If we whisper in the library, so it's about 40 decibel. 180, as you can see, is the loudest possible sound. and 160 is fire of shotgun, so it's really high, as you can see. Jet takeoff, of course, this decibel depends on the distance also from the source. So it's like for the jet takeoff, maybe it's about 50 meter from the source, because if you are very close to the jet, it's really more than this. As you can see here, side noise, noise has negative effects. So for example, it starts from when you are exposed to 65 decibels, so it can create it can cause mental and bodily fatigue if you are exposed to 65 decibel, even though it's a conversation almost here, right? But if for long term, it can create problem. 60 decibel for long exposure can cause permanent hearing loss for 60 decibel. Sorry, 90 decibel. So as you can see, 100 decibel, like here, loud music at disco, it can be really harmful. So this one, even short exposure can cause temporarily threshold shift. We'll talk what do you mean by threshold shift in the next slide. And 100 decibel, physically painful, must avoid, so you cannot really resist. This one, it should be 120. This one, instant loss of hearing, 150. Now, what do we mean by this temporary threshold shift? So within hearing loss, so there is two thresholds. So there is temporarily threshold, TTS, and there is PTS, permanent threshold shift. So for TTS, so temporarily hearing loss, and permanent threshold shift is permanent hearing loss. And so like this one, it results from destruction of some parts of the ear. So this one is really dangerous, and nobody wants this, of course. Of course, if you are always exposed to noise, we can even have some other side effects and health effects. We can be stressed in our working environment. We can have also psychiatric disorders because of noise. So it's not really something easy. And you know, in the cities, our cities nowadays, they are really full of noise. So it's the role of the architect to fight this issue, or to design building which is acoustically performant. Probably you know, in some countries, when people they go outside to protest, in some countries they bring water, and in some countries they bring sound cannon. So basically they create very high level of sound in front of the protesters, and it can be really painful, as you can see here. We call them, as you can see, long-range acoustic devices, LRAD. So as you can see, there is different models which can create from 137 decibels until 162 decibels. Remember, this kind of one, for example, it can make you lose your hearing. This one, and here is an example. As you can see, the distance is really far. For example, this one, it can reach, the max range is almost 9 kilometers. This one is 3 kilometers. far away from the protester, you can have an impact on them. Okay, now basically we went through the principles of noise, what is noise, how it behaves, how to calculate the intensity of sound, what is sound, and how to calculate the level of sound, how to calculate the combination of 3 or 2 levels of sound. We know that if we combine 2 levels of sound, it doesn't mean we just the first one plus the second one, but there is a logarithmic function that we have to use. But probably some that are asking why we need to know all these. We are doing architecture and we are building, we are focusing on design studio to build and to draw, and because there is what we call it acoustic. So acoustic, and there is acoustic in architecture. So what is acoustic in architecture? In the next video, you will understand what is acoustic in architecture. Next video is very important. And it's a TED talk, and they will ask you questions. I will just choose randomly, especially those their camera is off. I will choose them. If they don't respond, they will be absent. Okay, so the next video is about why it's important to study acoustic or to apply acoustic in architecture, to consider acoustic. So
Excuse me, sir. Sir, cannot hear the audio.
okay, you said you cannot hear, right?
Yes, sir.
Okay, thanks for that. Okay, I will try to, maybe because I dissect, no, I don't think. Okay, let me share again. Please, if you, I will play. If you don't hear anything, you let me know. Sorry.
It's time to start designing for our ears. Architects and designers tend to focus exclusively on these. They use these to design with, and they design for them, which is why we end up sitting in restaurants that look like this and sound like this, shouting from a foot away to try and be heard by our dinner companion. Or why we get on aeroplanes, which cost £200 million, with somebody talking through an old-fashioned telephone handset on a cheap stereo system, making us jump out of our skins. We're designing environments that make it. And it's not just our quality of life which suffers. It's our health, our social behavior, and our productivity as well. How does this work? Well, two ways. First of all, ambience. I have a whole TED talk about this. Sound affects us physiologically, psychologically, cognitively, and behaviorally all the time. The sound around us is affecting us, even though we're not conscious of it. There's a second way, though, as well. That's interference. Communication requires sending and receiving. And I have another whole TED talk about the importance of conscious listening. But I can send as well as I like, and you can be brilliant conscious listeners, if the space I'm sending in is not effective, that communication can't happen. Spaces tend to include noise and acoustics. A room like this has acoustics. This one, very good acoustics. Many rooms are not so good. Let me give you some examples from a couple of areas which I think we all care about: health and education. When I was visiting my terminally ill father in hospital, I was asking myself, how does anybody get waste that sounds like this? Hospital sound is getting worse all the time. Noise levels in hospitals have doubled in the last few years. And it affects not just the patients, but also the people working there. I think we would like for dispensing errors to be zero, wouldn't we? And yet, as noise levels go up, so do the errors in dispensing made by the staff in hospitals. Most of all, though, it affects the patient. And that could be you, it could be me. Sleep is absolutely crucial for recovery. It's when we regenerate, when we rebuild our cells. And with threatening noise like this going on, your body, even if you are able to sleep, your body is telling you, I'm under threat. This is dangerous. And the quality of sleep is degraded, and so is our recovery. There are just huge benefits to come from designing for the ears in our healthcare. This is an area I intend to take on this year: education. When I see a classroom that looks like this, can you imagine how this sounds? I'm forced to ask myself a question. Now, that's a little unfair. Some of my best friends are architects, and they definitely do have ears, but I think sometimes they don't use them when they're designing buildings. Here's a case in point. This is a £32 million flagship academy school, which was built quite recently in the UK and designed by one of Britain's top architects. Unfortunately, it was designed like a corporate headquarters with a vast central atrium and classrooms leading off it with no back walls at all. The children couldn't hear their teachers. They had to go back in and spend £600,000 putting the walls in. Let's stop this madness of open-plan classrooms right now, please. It's not just these modern buildings which suffer. Old-fashioned classrooms suffer too. A study in Florida just a few years ago found that if you're sitting where this photograph was taken in a classroom, row 4, speech intelligibility is just 50%. Children are losing 1 word in 2. Now, that doesn't mean they only get half their education, but it does mean they have to work very hard to join the dots and understand what's going on. This is affected massively by reverberation time, how reverberant a room is. With a reverberation time of 1.2 seconds, which is pretty common, this is what it sounds like.
In language, infinitely many words can be written with a small set of letters. In arithmetic, infinitely many numbers can be composed from just a few digits with the help of the symbol 0.
Not so good, is it? If you take that 1.2 seconds down to 0.4 seconds by installing acoustic treatments, sound-absorbing materials, and so forth, this is what you get.
In language, infinitely many words can be written with a small set of letters. In arithmetic, infinitely many numbers can be composed from just a few digits with the help of the symbol 0.
What a difference. Now, that education you would receive, and thanks to the British acoustician Adrian James for those simulations. The signal was the same, the background noise was the same, all that changed was the acoustics of the classroom in those 2 examples. If education can be likened to watering a garden, which I think that's a fair metaphor, sadly, much of the water is evaporating before it reaches, especially for some groups. For example, those with hearing impairment. Now, that's not just deaf children. That could be any child who's got a cold, glue ear, an ear infection, even hay fever. On a given day, 1 in 8 children fall into that group on any given day. Then you have children for whom English is a second language, or whatever they're being taught in is a second language. In the UK, that's more than 10% of the school population. And finally, after Susan Cain's wonderful TED Talk in February, we know that introverts find it very difficult to relate when they're in a noisy environment doing group work. Add those up, that is a lot of children who are not receiving their education properly. It's not just the children who are affected, though. This study in Germany found the average noise level in classrooms is 65 decibels. I have to really raise my voice to talk over 65 decibels of sound. And teachers are not just raising their voices. This chart maps the teacher's heart rate against the noise level. Noise goes up, heart rate goes up. That is not good for you. In fact, decibels is the very level at which this big survey of all the evidence on noise and health found that that is the threshold for the danger of myocardial infarction. To you and me, that's a heart attack. It may not be pushing the boat out too far to suggest that many teachers are losing significant life expectancy by teaching in environments like that day after day. What does it cost to treat a classroom down to that 0.4 second reverberation time? £2,500. And the Essex study, which has just been done in the UK, which incidentally showed that when you do this, you do not just make a room that's suitable for hearing impaired children, you make a room where behavior improves and results improve significantly. This found that sending a child out of area to a school that does have such a room, if you don't have one, costs £90,000 a year. I think the economics are pretty clear on this. I'm glad that debate is happening on this. I just moderated a conference in London a few weeks ago called Sound Education, which brought together top acousticians, government people, teachers, and so forth. We're at last starting to debate this issue. And the benefits that are available for designing for the ears in education, unbelievable. Out of that conference, incidentally, also came a free app, which is designed to help children study if they're having to work at home, for example, in a noisy kitchen. And that's free out of that conference. Let's broaden the perspective a little bit and look at cities. We have urban planners. Where are the urban sound planners? I don't know of one in the world. And the opportunity is there to transform our experience in our cities. The World Health Organization estimates that a quarter of Europe's population is having its sleep degraded by noise in cities. We can do better than that. And in our offices, we spend a lot of time at work. Where are the office sound planners? People who say, don't sit that team next to this team because they like noise and they need quiet. Or who say, don't spend all your budget on a huge screen in a conference room, place one tiny microphone in the middle of a table for 30 people. If you can hear me, you can understand me without seeing me. If you can see me without hearing me, that does not work. So office sound is a huge area. And incidentally, noise in offices has been shown to make people less helpful, less enjoy their teamwork, and less productive at work. Finally, we have homes. We use interior designers. Where are the interior sound designers? Hey, let's all be interior sound designers. Take on listening to our rooms and designing sound that's effective and appropriate. My friend Richard Mazouk, an architect in London, coined the phrase invisible architecture. I love that phrase. It's about designing not appearance, but experience, so that we have spaces that sound as good as they look, that are fit for purpose, that improve our quality of life, our health and well-being, our social behavior, and our productivity. It's time to start designing for the ears. Thank you.
Question time. Okay, let me check the camera is off. Okay, Sylvester just switched on his camera. So what did you understand from this video? Guma Sylvester, yeah.
We need to.
We cannot hear you well.
Hello.
Yeah.
Can you hear me? Yeah? From what I understand on the video is we have to consider about sound when designing the spaces.
Could you repeat, please? No.
Is it clear?
No. Could you repeat, please?
We need to design spaces considering the acoustic characteristic of the spaces. Meaning, like, if we design too open, it may distract others in their activities.
Okay, yeah, you are talking about the open space classes, right? He said it's madness. if we do it. Okay, good. You are following somehow. And as you have seen, one of his slides, he mentioned basically there is the sound source and the receiver, and he didn't mention the medium because he's not talking about building science, but instead of the medium, he said the space, right?
Yeah.
So for us as architect, of course, the space is very important, and the medium, when we are talking in the point of view of physics, we say the medium. So we mean the air or solid or gas. Yeah, but in a point of view of architecture, we mentioned the medium. So the one who took us to the sea, don't do that again. Where is Bavilina Young? Absent? Where is Bavilina Young?
Did you mean Baviliana Wong?
Oh, sorry, Baviliana. Yeah, that is A. Yes, are you? Where is your camera? I cannot see you.
My camera
has what?
Because I'm opening now.
Okay, so my question is, what are the negative effects mentioned by the speaker regarding noise? He mentioned many kind of negative effects, especially to our health. Could you mention some?
Unproductivity.
More, if you can.
And it also, for example, like the kids working in a kitchen and like the mom is cooking, right? So there's a lot of noise. So it's hard to focus on, the kids will be hard to focus on stuff.
But also he mentioned that lectures, for example, when there is too much noise, because about 65 decibels, right? When it is right, about 60 decibels, especially in classes, if students that are just talking and the lecturer is explaining the class, so one of the risks, the risk of even what they call it, heart attack can come just because of noise, because of exposure to noise every day. So even serious disease, they can come just from acoustic. So you as architecture students, you really need to consider also the noise, especially if your project is close to a highway or to an airport. It's really critical, because I have noticed in your design studio presentation, always I see sometimes projects they are very close to highways, and students they don't really care about that noise. They don't plan to they don't have any design strategies to prevent that noise, and this is what we will do in the coming classes. So today we have seen the overall, what do you mean by sound, acoustic, and noise, and all the metrics, and hopefully the coming class we will start talking about acoustic in architecture. So acoustic in architecture is the science of planning and building a structure to ensure excellent quality of sound to all the listeners. So that's the definition. So now we'll see who does that, who does the acoustic design, and well, what is architectural acoustic, why we need it, what are the issues that can happen if you don't do it, and how to do it. So basically the designers and listeners, room acoustic involves designing interior space to project diffused sound properly at appropriate levels with appropriate aesthetic qualities for music and adequate intelligibility for speech. As you know, the architect actually is one of the important stakeholders that they have to work on acoustic quality of the space. But of course, there is acousticians also. There is some people that are, especially when the project is a concert hall, where acoustic is very sensitive. Things regarding the vibration time that we will study, he mentioned in the video already. Because in concert hall, we need a specific vibration time, which we need to calculate it. So generally, acoustician, they do the details behind those calculations. But we also will see some basics here. So why we need architectural acoustic? Why we need to consider this? Because nowadays, you know, there is an increasing number of noise sources. It's not like most of buildings, you know, we are building inside the city, many roads, many vehicles, etc. Space planning exposed to noise sources, site plan, internal plan. So many buildings now, they are exposed to noise, especially buildings that are using glazing. And we have to consider also, you know, not any material is performant in terms of acoustic. After the next classes, we will see things regarding material and acoustic performance, things, for example, the absorption, sound absorption coefficient of material. So any material, actually, it has the sound absorption coefficient. Here's just an overall kind of strategies. You know, when there is a noise, we can, for example, reduce the source of noise itself, if it is possible. Otherwise, reduce noise transmission, for example, isolating the building, like using specific materials, maybe decreasing the size of windows which are facing the noise area, because window glazing generally is less performant than opaque materials like brick, etc. Also, we can reduce noise transmission. There is many kind of design features, like the one that we taught in lighting, like heliostat that we use for lighting to fix issues regarding lighting. Here for noise also there is, for example, we can install specific type of walls between, beside the road, the highway, for example. We can also plant trees, but trees that are not really efficient. If you plant just 5 meters of trees, it will not do anything. So you really need too many trees to reduce noise. So trees, they are not really efficient. We will see details in the next classes regarding this. We can also block exterior noise, or we play with the distance from the noise source. Can create buffer zones, especially using plants. We can also direct the sound. We can, instead of using shading device to protect the glazing from direct solar radiation, we can also install shading devices. We can install some walls to prevent noise, to reflect noise to another direction. Okay, basically this is the last slide. Well, this is not really important, but maybe You know this also, so regular and repeating pattern. So the result is music. Irregular and non-repeating pattern, this is noise. Okay, this is the last slide. So any questions? So as I mentioned, if you don't have any questions, I need to give you the, I need to show you the brief of the assignment regarding acoustic. So the assignment of acoustic, if you go to CN, you will find it. If you go to CN assignment, sorry, not this one. If you go to CN assignment 3, right? Architectural acoustic. So this one today we will submit it, and architectural acoustic is here. Please, if you downloaded this already, please download it because I did some update. Today is what, 16? So if you open this, you will find the truth in front of your eyes. I think no need to read, but basically it contains two parts. First part is group work. So you just keep the grouping of the previous assignments. And the second part is individual work, where you will need to propose a concert hall here in UCSI. So you have to read to understand. So please go to CN and read through it. I think no need to read for you. You just go and see what is written. If there is any issue, let me know. I will give you 10 minutes. So go to CN, assignment 3. You click here. Ten minutes, and if you have any question, let me know. All right, any questions? Everything is clear? So, as you have seen, this assignment, you will not use basically a case study like the previous one. So we need just to review existing projects and basically answer the questions in the brief. But the most important thing, you have to be careful to the plagiarism, because many students, they just go in SlideShare and they bring case studies there which have been done by other students. So SlideShare or any platform providing PDFs or presentations, you just copy and paste, it's not accepted. That's why it's important to show the reference, and I will see the reference. I will go to the reference and see. I find SlideShare, or because I remember those of SlideShare, because before last semesters many they did that, and I really didn't like it. You have to do the work by yourself. Better to do 5 pages yourself than bring in 40 pages, just copy and paste. And remember, it's 10%, it's 20%, right? The weight of this assignment. So 10% for group work and 10 for individual work, similar to the lighting exercise. So basically, we'll not need also any device like light level, sorry, light meter. Even though if you want, you can download it. You can try it in your room. I don't know why it's not working when I switch it on. When I started sharing the screen, it's not working. Before it was working. You can maybe you can just download it. So the sound meter, you download this one, and you try it. So basically, like in my room, it was 40 decibels, around 40 decibels, and it's written kind of quiet library. But now, when I started sharing the screen, it's not working. Oh yeah, I think because I'm doing this call, because yeah, this means probably even you it will not work because the microphone is working with Teams now. It should not be connected to another application using the microphone. Anyway, you can try it. I think it's very easy to try. No need for. So any questions, La? No questions? So I will give you the attendance form otherwise. Okay. So as I mentioned, today, 10 p.m., you will need to submit the assignment. You have 1 day for late submission. So please fill up the form. It's in the chat of Teams. So will you come back in March? We start studying face-to-face design studio. Sylvester, Kuma.
Sorry?
Will you start studying face-to-face starting from March?
You mean depends if the school allows though. I'm not sure.
Yeah, but normally there is people, they are saying from first they will come back students, at least maybe for design studio, no?
Yeah, for that one, I did put my name in the list to for tutorial, face to face.
Mm-hmm.
Yeah. I mean, it depends on the situation as well. Yeah.
Okay.
But I don't know. I think it's much better to understand if it's face to face. I don't know.
What do you mean better to understand if it is face to face?
If you're in the room, it's a bit not very.
Ah, okay. Yeah, and actually it's one of the reason I tell you switch on the camera, because if it is face to face, I see those, I can read your eyes if you understand or you don't understand. But like this, people, they are sitting below the seats here in the. So as you can see, many that are below here, they are staying. Someone is down here. So I cannot really know if you really understand or you don't understand. So what do you think about Design Studio? This one maybe it's okay. Overall, it's okay, but Design Studio, it can be really challenging.
Yeah. Yep.
So again, regarding the submission, of today, so please remember 10 p.m. Individual work will be submitted through CN. On the other hand, individual work and group work combined for each group will be submitted through OneDrive. I will give you the link later on. So prepare this. So you prepare individual work separated and group work and individual work in the end combined, everything combined. So in this way, when I go to CN, I see anybody who didn't submit the individual work, it will be easy for me to see those that didn't submit. Okay, I think. Okay. Okay, I think if you don't have any questions, you can leave the meeting. Bye-bye, take care.
Thank you, sir. Bye bye.
Thank you, sir.
Welcome, bye-bye.
新年快乐.
Those who didn't fill up the form, I see only 59, they filled up the form. Those that didn't fill up the form, they are absent, this means.
Excuse me, sir.
Yes.
I'm sorry, I had an unstable connection. So for the submission, everyone has to submit the individual work on CN and the group work?
In OneDrive, I will give you the link for OneDrive.
Oh, okay. So individual work, everyone has to submit on CN.
Exactly, yeah. But for OneDrive, you have to submit the group work and individual work combined, all of them, for each group, of course. For example, you are group 1, for example. So you take the group work and you add the individual work for all students in one PDF, and you submit. You understand?
Got it. Yes, sir.
I will
Thank
give
you.
you the link. I will give you the link, and I will let you know in WhatsApp when CN Dropbox is ready.
Okay, sir.
Okay.
Thank you.
Yes, sir.
Welcome. Yes.
I still don't have the access for the CN, so can I submit at the Google Drive the individual work?
Okay. Yeah. Okay. You can.
Okay.
But make sure is your individual work is connected with the group work also.
Okay.
Mm-hmm.
Thank you, sir.
Welcome.